Okay, this is Vincent DeSarno with quideo number 3. So, to start with the basic question, it asks, well, first it gives you a table of all these different car colors and the probability, the probability that a car will be that color in North America. Part A is asking, what is the probability that the vehicle you chose has any color other than the 6 listed? To find this, you just have to add up all the colors that are listed and subtract that from 1 to get your other category, and that ends up being 29.5. Okay, part B is asking what is the probability that a randomly chosen vehicle is either silver or white. So to do this, you just have to add together the probabilities of the silver and white vehicles, and you get 0.348, and that is 34.8%. Okay, part C is asking, when choosing two vehicles at random, what is the probability that both are silver or both are white? So to get this, you have to square the silver value and square the white value, and then add them together. And when you do that, you get 0.0606, which is 6.06%, and that's your probability that both will be silver or both are going to be white. Okay, so the next question, the advanced question, is talking about an experiment asking, will taking antioxidants help prevent colon cancer? It then kind of gives some more information about it, as in which vegetables are rich in antioxidants, such as vitamins A, C, and E. And it's asking, will taking antioxidants help prevent colon cancer? And then it says a clinical trial studied 864 people who were at risk of colon cancer, and the subjects were divided into 4 groups. After 4 years, the researchers were surprised to find no significant difference in colon cancer among the groups. Part A is asking, what are the explanatory and response variable in this experiment? So the explanatory variable is going to be the antioxidants, and the response variable is going to be colon cancer, or risk of colon cancer. Part B asks to outline the design of the experiment and use your best judgment in choosing the group sizes. So the first thing I did was assign each person a number from 1 to 864. Then you use a random number generator between 1 and 864 and pick out 216 people for group 1, and then you do this for the remaining 3 groups while skipping any repeating numbers. Once you do that, you give each of the subject groups a different antioxidant, and then finally you compare rates of colon cancer between all the groups. So part C is saying to assign labels to the 864 subjects and use table B starting at line 118 to choose the first 5 subjects for the beta-carotene group, which is also the first group. So to do this, I assigned them between 001 and 864. Then starting at line 118, I went and going across, I found the numbers to be 731, 253, 304, 470, and 296. Okay, part D says the study was double-blind. What does this mean in the context of this problem? So double-blind means that neither the researchers nor the subjects know who is taking which antioxidant, so there's no bias in the data. Okay, finally, part E is asking to find some lurking variables that could explain why people who eat lots of fruits and vegetables have lower rates of colon cancer. So, these variables are going to be variables relating to having a healthy lifestyle. That could be people who exercise or people who don't exercise, and mainly people who eat healthy and eat lots of fruits and vegetables compared to people who eat lots of probably junk food and fast food, as well as people who might already be at risk for colon cancer. Okay, the AP question is talking about 2 different antibiotics curing ear infections in children. So antibiotic A is known to effectively cure the infection 60% of the time. Treatment with antibiotic A costs $50. Antibiotic B is known to effectively cure the infection 90% of the time, and treatment with antibiotic B costs $80. The antibiotics work independently of one another. Both antibiotics can be safely administered to children. A health insurance company intends to recommend one of the following two plans of treatment for children with this ear infection. Plan 1 is to treat with antibiotic A first. If that is not effective, then treat with antibiotic B. Plan 2 says treat with antibiotic B first. If it is not effective, then treat with antibiotic A. Okay, Part A says if a doctor treats a child with an ear infection using Plan 1, what is the probability that the child will be cured? If a doctor treats a child with an ear infection using Plan 2, what is the probability that the child will be cured? So, the first thing I did was set two events. One event A equal to antibiotic A working, and one event B is antibiotic B working. So, to find the probability of the first cure, you have to do the probability of antibiotic A, and then add that to the probability of whatever isn't antibiotic A, and multiply that by the probability of antibiotic B working. So then you have 0.6 for antibiotic A, and then 0.4 for what's not antibiotic A, and 0.9 for what's the probability of antibiotic B working. So when you do that, you get 0.96. Then for cure number 2, you do basically the same thing, but switch around the probabilities. So you do probability of B plus the probability of things that aren't B times the probability of A. So you get 0.9 plus 0.1 times 0.6, and that also equals 0.96. They are the same probability. Part B says, compute the expected cost per child when Plan 1 is used for treatment. Compute the expected cost per child when Plan 2 is used for treatment. So to do this, the first thing you have to do, well, first I looked back at the prices, so we know that antibiotic A costs $50 and antibiotic B costs $80. So to find the cost of the first plan, you do $50 times 0.6%, or 0.6, because that's the probability of A working times its cost, and you add that to the probability of B working times the cost of A plus B, because you already would have used treatment A, which costs $50, plus the treatment B, which costs $80. That ends up being $30 plus $52, and you get that treatment A costs $82. Then to find the price for cure number 2, you do, again, basically the same thing. So $80, because that's the cost of antibiotic B, times 0.9, because that's the probability of antibiotic B working. Then add that to 130, because that's the two antibiotics together, times 0.1, because that's the probability of antibiotic B not working. So then you get 0.72 plus, or not 0.72, $72 plus $13, and that is equal to $85. Finally, Part C is asking, based on the results in Part A and B, which plan would you recommend? Explain your recommendation. I would recommend Plan 1. So the probability of both plans working is the exact same. They're both 0.96. So since they're both the same probability, you have to look at other criteria to determine which one is better. So Plan 1 only costs $82, while Plan 2 costs $85. So it's going to be better to use Plan 1 since it costs less money, but has the same probability of working.